From the Library of Congress in Washington, D.C.
I'm Steph Marcus from the Science, Technology, and Business Division, and I want to welcome you to the second lecture of our 2018 series. Our next one will be May 15th, and that's going to be on water security, using satellites to monitor water around the Earth. Mars is always popular, and it seems like just recently we had a talk on MAVEN, another Mars mission that was called Case of the Missing Martian Atmosphere, but that was in 2014, and our speaker was on that team, and he's also going to be on the upcoming Mars 2020 team if we get the money. So right now he's all involved with the Rover Curiosity, and today we're going to hear about the 5 years of information that we've got from Curiosity. Speaker is Dr. Scott Guzewich.
Thank you.
I bet none of you guessed how to say his name, but I'm glad I learned it's Guzewich. And he was a weather officer in the Air Force, so a little bit different background from some of our speakers. He got his degree in meteorology from Penn State and an MBA from Cameron University, and then finally his PhD in Earth and Planetary Sciences from Johns Hopkins. So let's get started and hear about Curiosity. Thank you.
All right, thanks, Steph. All right, so hello, everyone. I'd like to talk to you about the last 5 years that we've explored Mars with Curiosity. I'm a member of the Mars Science Lab science team. I've been a team member since just after landing, and today we'll talk about swimming in Martian lakes. So what I want to start with a little bit here is we're going to go in the Wayback Machine, and we're going to kind of talk about our history of Mars over the last century and why we are exploring Mars today with Curiosity and how much we've progressed over the last 100 years. I mean, literally in my grandparents' time, this was the vision of Mars that we had. And it's pretty remarkable when you think that just within a generation or two, we've gone from having a spacecraft on Mars, multiple spacecraft on Mars at the same time, exploring Mars, to having people like Percival Lowell peek through telescopes and then hand draw pictures of what they think they saw on the surface. And the sort of work by people like Percival Lowell really captured the imagination, because he imagined, sort of with a mistranslation from an earlier Italian astronomer, Schiaparelli, that there was these canals on Mars, that the Martians were living on a dying world, bringing water from their receding polar caps down to their drying farms at low latitudes, and that this was sort of the vision of Mars that then captured the public imagination, fueled science fiction, things like Orson Welles' famous radio broadcast, and this was the vision of Mars that most of the public had. And so, we kind of imagined not only was Earth populated, but of course Mars must be populated, Venus perhaps too. This was the place that we thought we came from. And it really only a couple decades after this, not long after Percival Lowell died, we went from this vision of Mars to having a space program where we could think about actually sending a spacecraft, as primitive as it may have been, to Mars to see what Mars was like truly there, and the planet. And so early here in the space age, in the early 60s, it was actually the Soviet Union that was trying to do most of the Mars exploration and unfortunately failing miserably for the most part. They sent, actually the Soviet Union and Russia has never had a successful Mars mission. But they sent a number of Mars missions here, and they either all blew up on the launch pad, a couple actually made it into space and then failed at some point during their transit to Mars. Of course, in the US, we also had some failures as well. And note though here that a lot of these in the early days of the space program were launched in pairs. They built things redundantly. They had two of the same spacecraft because they knew a lot of their rockets blew up, a lot of their spacecraft failed. And so, the Soviet Union would launch things in pairs. We would launch things in pairs as well. So Mariner 3 here was a launch failure, but thankfully the next one was not. And that was Mariner 4. So Mariner 4 was the first spacecraft to actually make it all the way to Mars. This was a flyby mission. So we have sort of a philosophy in planetary exploration where we fly by, we orbit, we land, and then we rove. So flyby means just take the spacecraft, shooting past the planet, and hopefully taking as many pictures or pieces of data as we can as we go by. And early days here in the early 60s, this was 1965, Mariner 4 flew by and took 20 pictures 20 pictures. We take hundreds with Curiosity every single day. 20 pictures was the whole breadth of our exploration from Mariner 9. And take a look at this image here. This is one of the images. Now, we knew what the moon looked like, right? We've been looking at the moon now with spacecraft and telescopes at this point in 1965. We knew the moon was a dead place. But we still had that hope that maybe Mars was at least something like what Lowell thought it was. Maybe there's not civilizations, but there's at least maybe plants, or there's microbes, or there's something there that's not the moon. And so Mariner 4 flew by and saw this. And I've asked elementary school kids, what do you think this picture is? And they say, the moon. And it's like, well, exactly. And that's what everybody thought. It was like, oh, we actually found Mars as just a big, giant red version of the moon. And so without waiting for any more data, the New York Times confidently declared, Mars is dead. That's it, folks. It's over. Mars is dead. We don't need to bother anymore. President Johnson was so glad that he was not going to be invaded by Martians because he was terrified from the 1938 Orson Welles broadcast. So he's like, okay, good. Not going to be invaded by Martians. Only have to worry about those Soviets. And but then Carl Sagan here pointed out, now, 20 pictures at 1 kilometer resolution. So most of your good weather satellite data is 1 kilometer resolution. So can you see any people or even cities really at 1 kilometer resolution? Not so much, You can see plants because we know what the color change is from fall to spring and that sort of thing. But you don't see any animals. And so Carl Sagan quipped here, if there were kilometer-long elephants covering the surface of Mars, we wouldn't have seen them. But actually, this sort of disappointing result actually did result in a reduction of funding for Mars exploration in the late 60s. But not enough, thankfully, to kill the program, because we actually sent Mariner 9. And what Mariner 9 did was actually went into orbit around Mars. And so this was key, because instead of just flying by and shooting a bunch of pictures as fast as possible and then shooting off into space never to be heard from, Mariner 9 went into orbit. And it went into orbit at a very particular time where it was lucky it went into orbit, because if we had just flown by, all we would have seen was this giant dust storm, which is what actually I study. But there was this huge global dust storm on Mars when Mariner 9 arrived in 1969. And these dust storms occur periodically on Mars where the whole planet is shrouded in this dense haze of dust and you cannot see the surface at all. And so imagine if it had just been shooting by, we would have just seen these murky photographs with no surface features whatsoever. But luckily it went into orbit, and so it could wait until the dust began to settle and the dust dissipated. And as the dust was beginning to dissipate, we saw these 4, actually, one's off the screen here, but these 4 giant little spots on the surface here. And what these are volcanoes. And these volcanoes are so large that they actually essentially stick out of the atmosphere into space. The one volcano that's off screen here is 3 times the height of Mount Everest. And this mountain essentially sticks above the surface of the planet so far that the atmosphere is essentially all below the top of the mountain. And so the volcanoes stick above this layer of dust, and so we could see these. And then as the dust began to settle, we finally began to see Mars as a real place. And we saw amazing features like this here. This is an ancient river valley called Nergal Vallis that looks anything like a river valley here on Earth, the Nile, the Amazon, Mississippi, whatever the case, all these branching tributaries and things like that. And we finally realized Mars is not the moon. It's not Earth, but it's not the moon. It's a distinct place all to itself. And soon after, in the mid-70s, we sent Viking. And Viking not only orbited, but landed 2 spacecraft. This is surface frost here on a cold morning, just like we have here in DC or Maryland on a cold winter morning. We get frost on the ground that then evaporates or sublimes during the afternoon. Same thing here on Mars where Viking landed. And we finally saw Mars is a real place unto itself. It's a unique planet with unique properties and maybe an amazing history that we don't quite understand yet. So Viking went primarily to find life. So we knew by Mariner 9 here, okay, we're not finding any civilizations, we're not finding any giant forests or anything like that, but there's still maybe good reason to think that there's microbes in the surface. We know there's water in the polar caps, there's water in the atmosphere, maybe there's liquid water sort of percolating in the soil, and maybe there's still microbes. So that's what Viking was sent to explore. And Viking landed and had very specific measurements that they were taken to test for life. And the most famous of these, or perhaps the most infamous, was called the labeled release experiment. So what this did is it scooped up some soil, and it put it in a little chamber. And of course, microbes need to eat, right? So they fed the microbes with a very specific type of food and water that was marked with a certain radioactive isotope. So presumably, the microbes would eat this radioactive food, and then they would respire and kind of breathe this back off in there, and then that respiration would be tested for. And they did several of these. And so here's a kind of a control experiment, right? Nothing happening. Didn't feed anything to the soil, nothing happens. You feed something to the soil, and boom, you get this huge response, which would suggest that there is tons of living microbes in the Martian soil. And of course, this was understandably exciting. This is exactly the sort of result that people would have expected. But thankfully, we didn't just send the labeled release experiment. There was other tests that we did to the soil to see, okay, there should be other things, other properties that living things would have in the soil. And so one of those was called a mass spectrometer. And that's designed to basically test what the soil's made of. And so every living thing on Earth has organic molecules, carbon-bearing molecules in it, right? And so you should have tons of carbon-bearing molecules. If the life is like Earth, you should have all this carbon-bearing material in the Martian soil. And not one organic molecule was detected, not one. And so there was this puzzling contradiction here. You have this seemingly very positive experiment, but then you have every other sign, not just this one, but every other test saying that there's no life at all, and not even like a hint of it. There is nothing there. So you have a very positive and then like 3 very negative results. And this was very puzzling for obvious reasons. And actually, Gale Crater, the PI here, still insists that the labeled release experiment found life. Still insists because he believes there's some other problems with the other experiments. But his opinion is certainly in the minority. And we have a pretty good understanding of why these experiments gave the results they did now with more knowledge. But you can imagine here. So we went there looking for life, and the general consensus was we didn't find it. Mars truly is dead, and that was pretty disappointing because Mars was sort of the last hope in the solar system at that time, or so we thought. And so we kind of went to this long pause, essentially 20 years, where we didn't send a mission to Mars. And there's obviously some other reasons why that probably happened, but certainly scientifically was because Viking was sort of disappointing in that way as far as searching for life. There were certainly lots of exciting things about maybe Mars a long time ago, but nothing today. And so the only spacecraft launched over a 20-year period from 1975 to 1996 was Mars Observer in 1993. This was a very capable mission, and it got literally within 3 days of Mars, and then it did not turn out well. And the general consensus is there was a fuel line that somehow got ruptured and basically shot it off in an opposite direction. It lost radio contact with Earth and never to be heard from again. And this was a pretty big mission, so that was disappointing. Obviously, this was the first Mars mission in a long time, and during a period where NASA was not sending a lot of planetary missions. Nowadays we're sending usually 1 or 2 per year, knock on wood, and we're not doing that as much 20 years ago. So that was pretty disappointing, but soon afterwards, we had a very exciting moment occur. And this was a very formative moment in my life. And if any of you were kind of alive and paying attention to the news in 1996, particularly in the summer of 1996, you would have remembered this because this was on all the news channels. And I was at the beach at this time on a vacation with my family. And I was glued to the TV screen. I could not pull myself away from this news, which was that this rock, a Martian meteorite, had evidence of life in it. And so this rock is called ALH 84001. So this designation is how they assign names to meteorites. And it's basically because this was found in Allen Hills, Antarctica, in 1984, and it was the first one of the season. So every summer in Antarctica, winter here, we send a team of scientists down to Antarctica to collect meteorites. And so why are meteorites really easy to find in Antarctica? Because this is brown and Antarctica's white, right? So they stick out. I guarantee you there are meteorites here in DC, not far away, but I couldn't find them for you. They don't look any different to me than any Earth rock. But in Antarctica, the only thing there is meteorites. And the way the glacier flow, actually, so these meteorites sometimes actually get incorporated into the ice, get buried by a lot distant, hundreds of feet down into the ice. And then as the glaciers flow up against these mountain ranges, they sort of get kind of pulled back up. And there are fields essentially full of meteorites just sitting there where these glaciers sort of kind of let them deposit as the ice sort of evaporates away against these hills. And so there's certain places here. One of my colleagues just got back from this a few months ago. Teams go down to these certain places and collect meteorites. And the reason, when this was first found, it was actually thought to be a lunar meteorite. And the reason we know this came from Mars is because we sent Viking there. And we know what Viking found Mars to be made of. And we said, hey, okay, this is what Mars is made of. This is Mars. And we've only found a few of these Martian meteorites. There's literally like a couple dozen, and some are actually kind of probably from the same rock. What's unique about ALH 84001 is it's very, very old. It's like 3.5 or more billion years old. And we can do that by various tests to see what the ages are of the various materials in there. That this is a very ancient rock that was formed at a time when probably Mars looked a lot more like Earth. And so that alone made it very exciting. But then they started digging into it more, and they found certain chemistry that on Earth is, at the time we thought, seemingly only produced by biology. And don't ask me what those things are because I'm not a biologist, but there were certain things in there that are only produced by living things. And then, of course, what got all the press was this picture. This is an electron microscope picture of what looks all the world like some sort of worm fossil. The difference, of course, being that this is tinier than any microbe on Earth. This is nanometers long, extremely tiny, but sure looks like a worm to me, right? So this is the fossil that we found in the Martian rock. And, of course, this was basically all over the news. President Clinton made a statement there at the time, and this is really what drove me to want to study Mars, because this just kind of captured my imagination. And instead of being out there on the beach enjoying my vacation, I was watching TV in the room, all about a Martian meteorite. And so this really kind of kick-started a new era of Mars exploration, because at about the same time, in 1996. We launched the little plucky Sojourner rover here, which landed on July 4th, 1997. And just for a sense of scale here, Sojourner is about the size of a small microwave. So, and then the Spirit and Opportunity rovers, this is Spirit as seen from orbit. Spirit and Opportunity sort of, go up to about here and, maybe cover sort of this whole area around the speaker's lectern. And then Curiosity is essentially a Mini Cooper. So that's your sense of scale word, kind of moving up there. And what really changed then in 1996 was we had a Mars exploration program. We didn't have these one-off missions. Viking was 2 missions, but it was sort of a one-off. And then we went 20 years. And then we had Mars Observer, which was a one-off, and it failed. So nothing happened. And then we said, hey, we're going to have a whole program that's going to follow the water. That was the catchphrase. And we're going to learn about the history of Mars, and we're going to understand where the water went. Did Mars have life long ago? And this started all kind of with the little Sojourner rover there. And then we sent orbiters, the orbiter looking down here on Spirit from above. So at the same time, we finally had things active on the surface and active in orbit. And that's really key, because you get the sense of perspective that's totally unique that you can't get from either place. Of course, if you're on the ground, you're in one little spot, right? I mean, how much could DC tell you about Earth? I mean, honestly, if you took away all the buildings and everything, I'm not a geologist that well. I don't know much. But how much could DC tell you about Earth? Could it tell you about deserts? No. Could it tell you about oceans? No. Could it tell you about the polar caps? No. One little place on Mars, how much can it tell you about the planet? But then you get that in situ knowledge that then you can use from orbit to kind of extrapolate to the planet. And you get a much broader perspective. And that's what having a program really offered us. So that kind of went for a few years, and now we got to about 2003. And so this is what we knew by that point. We knew Mars once had flowing liquid water. This is an image here of an ancient river delta, and it looks all the world like what you would see if you looked at a satellite image of the Mississippi flowing out into the Gulf of Mexico. You see these sort of branching patterns. In southern Louisiana, you get these branching canals and networks of things as it flows out, and sort of new channels form constantly, and it moves around. And that's exactly what you get here on Mars. But of course, it's all dried up. There's nothing there now. But long ago, there was something there. And we can tell by just the shape of this delta, the way these different channels kind of cut over each other and are deposited on top of each other. We know that this actually lasted for a long time. This was not just a one-off giant flood that then evaporated immediately and was gone within a few months. This took time. This took a lot of time, decades, millennia, maybe even more. We knew Mars once had a magnetic field. Magnetic field on Earth protects us from the solar wind. So the solar wind is constantly trying to kind of strip away our atmosphere. And because the Earth is bigger, that helps too. But we have an active magnetic field that kind of pushes all of that charged particles away from Earth. And if any of you were here for the MAVEN talk a few years ago, that's what happened to Mars, basically. The magnetic field went away, and the whole atmosphere was basically stripped off into space, just pulled away over billions and billions of years. And it's still happening today. Mars is still losing atmosphere today. And so we knew Mars once had a much thicker atmosphere. We didn't know how thick, but we knew it was thick enough to allow liquid water to flow on the surface. And you need to have some amount of sort of heft to the atmosphere to allow that to happen. It can't happen today. And so this was 2003. And so what kind of became was the idea for the Curiosity rover, which would have been a step up. At the time was going to be a more incremental step than what it ended up turning out to be, but an incremental step above Spirit and Opportunity. Because what we wanted to answer was, how long did the liquid water last? Was this really like a flash in the pan, decades, intermittent type thing, or was this a long-term thing where life would have had time to evolve perhaps? How long did that thicker atmosphere last? These kind of go hand in hand. And even if liquid water was there, and even if the atmosphere was there, was the environment truly habitable? Was this some sort of like acidic, boiling mess that only like the most extreme life forms on Earth can survive in? Or was this something much more temperate, kind of what we hope, which is much more temperate, clement environment where all manner of life could live, at least as we understand it here on Earth? And then was the chemistry right? Did we have the different ingredients that life needs? Life needs a whole host of different chemical compounds to live. It's not just carbon, it's not just water. There's phosphorus, there's nitrogen, there's any number of different things that life needs to have the different pathways form chemically, to have sources of energy to live on. And so was the chemistry right? And so we said, okay, so this is what the next mission is going to address. This is what Curiosity will address. It wasn't called Curiosity at the time, it was called the Mars Science Laboratory, which it still is. But that was what this mission would accomplish. And so as we packed on all these instruments, or what we wanted to put on it, we said, wow, this thing's going to be pretty darn big. And unfortunately, when it's pretty darn big, we can't land it the same way that we landed things before. So before, with Spirit and Opportunity and Sojourner, we had these giant airbags. Anybody ever seen videos of how, or sort of artist conception of how these landed? It's pretty wild, right? I mean, they're all kind of wrapped up in these airbags, and then the parachute is descending through the atmosphere and essentially just drops it off. And it just bounces and rolls and eventually settles down. And the airbags deflate and this thing sort of clamshells open. And then the rover just sort of stands up in the middle of this and drives off. Well, Curiosity is way too darn big. There's no way for Curiosity to fit in airbags that could survive that sort of thing. It's just too much force that would hit on the ground. And so we need to come up with a whole new way to land Curiosity. And what the engineers at JPL in their infinite wisdom came up with is called Sky Crane. And the first time I saw this, I said, this is the craziest thing I've ever seen in my life. There's no way this is going to work. And I was telling Steph, I've now seen crazier things, which makes me even more concerned. But, and the JPL engineers will kind of famously say, this was the least crazy thing they came up with. This was the least crazy thing. And so we'll show you a video of how this works here. But basically, there is no packaging for Curiosity. Curiosity came down, wheels down, and that's it. And it was ready to go. So okay, we had a mission. We knew what we wanted to do with it. We had a new way to land it on Mars. And then the question is, where do you put it? And this is a question that we're actually deciding right now for the next mission. So Curiosity's twin sister, almost twin sister, they're fraternal twins, is going to be launching in 2020. And we're now down to three candidate landing sites for the Mars 2020 mission. And it'll be decided here at the end of the year where of those three it will go. And so similarly, there was a long list of candidates for Curiosity. And it's not just science that drives this, there's engineering requirements too. So Mars's southern hemisphere is a lot higher altitude than the northern hemisphere. And there's just not enough air to slow us down enough. You need more air just to slow us down as we're entering the atmosphere. So we can't land in the southern hemisphere, at least too far south. And we can't land on high mountains. And we don't want to land in the really crazy places like valleys that have lots of rock walls and dangerous things around them. So we need somewhere that's safe to land at a low enough elevation, but also scientifically interesting. And when you kind of black out the parts of the planet that's not safe to land on, you're not left with that much. I mean, you're kind of left in this narrow band, roughly near the equator, kind of minus 5 or 10 degrees south to like 15 or 20 degrees north, and at elevations below like a kilometer or two, kind of below Martian sea level. And so in that list, eventually Gale Crater kind of rose to the top. And the reason is because it had all these different chemical compounds, clay compounds, sulfates, things like that, that on Earth indicate the presence of water and different types of water and different ways that water has interacted with the rock. There was evidence that there was this river valley that sort of had flowed into Gale Crater and maybe left some sort of delta here or fan. And so there's sort of different signs that water had played a big role in Gale Crater. And so this is why Gale was eventually selected. And this is sort of an artist's conception of maybe what Gale looked like billions of years ago. And this is sort of a Earth-like, or a picture of Earth here at a high mountain lake of maybe what you can kind of use as an analogy. So probably kind of salt. Maybe was it salty? It's possible. But you have not a lot of living things around it here. There actually are some plants there if you look closely. But this is sort of what maybe Gale looked like, 3.5 billion years ago or more. And so, okay, we had a place to land, we had a mission, and then I want to show you this little video here, which I think really kind of shows well the whole evolution of the mission and the work that went into it. I mean, this was 2003 that the mission was first conceived of, and now it's 2018, and we only landed in 2012. So there's a huge amount of time that is take to build these missions, to develop the science case for them, and then to go ahead and actually get them to Mars. Oops, let's go back.
That great things take many people working together to make them happen is one of the fantastic things of human existence.
Not only have we driven the rover, we've removed its arm, put it all through its paces, but it's been in a thermal vacuum chamber and kept very cold. Parts of it have been in a centrifuge. We've done drop tests, pull tests, drive tests, load tests, stress tests. It's just an amazing amount of testing this vehicle has gone through. We've tried every way of operating the vehicle using the software, literally thousands and thousands of hours of software testing. It's been just an amazing several years, really, of constant testing and development, finding problems, fixing those problems, and going on to the next problem. I think she's ready to go.
LC, this is the LD on Channel 1. LC, you have permission to launch.
Roger, proceeding with the count.
T-minus 10, 9, 8.
7, 6, 5, 4,
3, 2,
1.
Am I confident that she's going to go and she's going to be successful? Absolutely. It's going to go and she'll be good.
We should have parachute deploy around Mach 1.7. The parachute is deployed. We are decelerating. Heat shield has separated. We're on the ground. Standing by for back shell separation. We are in powered flight. We're at an altitude of 1 kilometer descending. Standing by for sky crane. Sky crane has started. Touchdown confirmed. We're safe on Mars. Time to see where our curiosity will take us.
What a fantastic demonstration of what our nation and our agency can do. I could only think of the words of Teddy Roosevelt as I was sitting there. It is far better to dare mighty things even though we might fail, than to stay in the twilight that knows neither victory nor defeat. And the team brought us victory today.
Today, right now, the wheels of curiosity have begun to blaze the trail for human footprints on Mars. This is an amazing achievement.
Well, today on Mars, history was made on Earth. The successful landing of Curiosity marks what is really an unprecedented technological tour de force. It will stand as an American point of pride far into the future.
We've got a long mission ahead of us, and because of that and the capabilities of this rover, we have this possibility for just monumental science accomplishments.
Within 2 months, the team found an ancient riverbed, evidence of flowing water.
Give you guys the end of the story too far. But if you saw during the video there, this is a picture. So Curiosity has a camera underneath it called the Mars Descent Imager, or MARDI. And so MARDI took a video basically as soon as the heat shield came off, and here it is floating down, never to be seen again. It took a video all the way down to landing, and it's pretty remarkable. You can look it up on YouTube. But here's another image here. So this is the rocket boosters there you saw on the side sort of shooting off, and it kicked away all the dust from the surface right in the spot that the rover was about to touch down on. And so you saw all this dust being kicked away. And then this is one of the first pictures that came back. This is we have 4 cameras kind of pointing to the front called hazard cameras, looking for rocks basically. We don't want to drive over anything big and sharp and pointy. And this is one of those cameras. So looking out, seeing the shadow, it landed kind of towards sunset. And here's the center of the Gale Crater, this giant mountain, which we called Mount Sharp, and sort of where we were headed from that beginning. So it was pretty poignant image that, this is sort of the journey ahead as soon as we touched down. And I was an active fan here watching from home before I was a team member. And if you look real closely, this shirt is not brand new. So this was 2012. So Curiosity was supposed to launch originally in 2009. And there was technical problems like happens in space because space is hard. And so I bought this shirt like back in 2008. So this was already like 4 years old when we finally touched down. But it worked out, thankfully. And Sky Crane worked, and hopefully it'll work again a few more times because they're going to use it again in 2020, and even want to use it again if we ever land something on Jupiter's moon, Europa. And so here we are. And again, this is sort of why it's so important to have a Mars exploration program, because this is a camera looking down, the high-rise camera on the Mars Reconnaissance Orbiter, which has been there for 12 years already and is working great, and looking down here and seeing the rover tracks. So here's all the dust that got kicked away from the spot. You can see like the burn marks basically from the rocket engines on the surface. And then you can see this little faint track that went over here to this area called Yellowknife Bay. And if you recall from earlier on, we wanted to get up the mountain because that's where all these clays and things like that, these materials that showed that water had once been present, were all up high on the mountain. That's a long way from where we landed. And we couldn't land on the mountain. It was just not safe enough. So we landed in this flat spot, sort of in the middle of the crater. And we always knew we'd have to drive a pretty far distance. But we went here just a few weeks after landing over towards this area called Yellowknife Bay. And this was believed to be maybe just a sort of an edge of where that possible river delta kind of flowed out into Gale Crater at some point. And I wasn't even on the team at this point. I joined like very soon afterwards. But I don't think that anyone truly expected to find what we found in Yellowknife Bay. So one of the first things that we found were these types of rocks. These are called conglomerates. And you can see here there's all these little embedded rocks in the bigger rock. There's little chunks rounded. In particular, they're all rounded. So if you go in a stream bed here on Earth, they're all kind of rounded because the water has flowed, they've kicked up and knocked against each other, and all the jagged edges have been smoothed down over time. And a long time. It doesn't happen in a day or two. This happens over years. And these rocks are all smooth, and then they're all kind of congealed together into one giant rock. And again, that's by the action of water. And we get the same thing here on Earth. I mean, if you handed me this and you dusted off all the Martian red dust, and you handed me this from Earth, I couldn't tell them apart, that's for sure. But these are the same sort of processes that are occurring on Earth and Mars. You have a stream bed that's flowing over, rounding these pebbles out, and then kind of congealing them together into one rock. And again, this is because this area, so that's where we landed, and we drove just over here. It was on the very edge of this, what's called alluvial fan. So this kind of delta, this river valley here called Peace Valley has flowed out into presumably this lake or the end of the river, maybe just to kind of dried up. We didn't know at the time. But it reached all the way down here that the stream bed, or what was left of the stream, and this was not just sort of inches deep water. This must have been a few feet deep at the very least to create that sort of flow. You can't just have it from a little bit of a trickle. You need to have a true stream or river to create that sort of motion to round those pebbles out. So similarly, we found these very fine layers here. You can see they just kind of peel away almost like, phyllo dough from like a baklava or something, right? They're just very fine layered materials. And you can see here, there's, very small scale. These are like millimeters thick sometimes, or centimeters at most. And they're all kind of peeled away and then kind of get jumbled around over time. But again, this shows that you have sediment. So again, you have suspended in a river, you have little tiny particles, right? Sand particles, dust particles, whatever, suspended in the flow. And over time, they sort of settle out. And so again, like the Mississippi River, you have all these deep layers of very fine sediments that have been deposited over long, long periods of time. Kind of muck and mire that is then kind of solidified into rock. And again, here on Earth, this is sort of an ancient lake bed in Scotland, 400 million years old. And it's the same sort of thing. Now, these have been tilted up by other geological activity over time, but you see this very fine layering in this material here in Scotland. And it's the same sort of thing we saw here on Mars. So again, another piece of evidence that, hey, that this was something that happened over long periods of time. This was not a flash in the pan. This was not days, weeks, months. This was years and maybe millennia. So we were the first time, Curiosity has a drill on it. And this is the first time we've really drilled into Mars and found that Mars has this very peculiar color here. Mars is not red, it's gray. Much more Earth-like, lunar-like gray here beneath this red Martian dust. And now that we've drilled a couple dozen times, there's actually different colors of different rocks. We found like purplish colored rocks, these more gray colored rocks. Some have kind of a greenish tinge to them even. And we've drilled in here and then been able to sample these inside Curiosity's laboratory. One of the handouts out there is one of the instruments, the big instrument on Curiosity called SAM, which was built at Goddard. And I'll show a slide here. The next slide is actually about SAM. But we take this material here, we scoop it up, and we deliver it in very small doses into the instruments that are inside Curiosity's body. And then we can really tell what these are made of. So we did that. We dropped pieces of it into it, and the point is here that there's that water came out of this, there was oxygen, there was sulfur-bearing compounds, and the different temperatures that these come off of are sort of indicative of what this is made of. We can tell what the mineralogy is of these materials. And what I particularly want to highlight are this material called carbonates. So carbonates are extremely common here on Earth. The cliffs of Dover, these cliffs of Normandy here, you have hundreds of meters or hundreds of feet thick carbonates. And there's nothing magical about how these are formed. Now, they can be formed by living things, by little creatures in the ocean have like carbonate shells, and they kind of fall out into the bottom of the ocean. And over time, like the whole bottom of the ocean is essentially nothing but tiny little fossils of microbial life from the ocean. But they can be formed without biological activity as well. All you need is water and then carbon dioxide in the atmosphere. And the chemical reaction occurs by itself, and it turns to rock, and turns to carbonate rock. And so from long ago in Mars exploration, we knew, okay, if Mars had a thick atmosphere, presumably it was carbon dioxide. Venus's atmosphere is all carbon dioxide. Earth's early atmosphere had a lot of carbon dioxide. Mars's early atmosphere probably had a lot of carbon dioxide. And it would have needed to, if it was going to be as warm as it would have been necessary, to have liquid water. So there should be just an absolute ton of carbonate rock on Mars, because presumably Mars, all that atmosphere got locked into carbonate rock at some point. And we've looked and we've looked and we've looked and we've looked, and there is not giant cliffs of carbonate rock on Mars. And if they're there, they're hiding really, really well, because we've looked everywhere. And so we wanted to know, like, okay, there's little bits of it. We found little bits. So, but where did the rest of it go? I mean, if there was this huge, thick atmosphere, as thick as Earth's atmosphere today, and it's all gone, and it's not buried in the rocks, the only place it really could have gone is space. And this is actually an image from kind of a graphic figure from the MAVEN mission, that mission that's studying the upper atmosphere of Mars and how it's losing atmosphere today. And so, but using the combined work of MAVEN studying up at the top of the atmosphere and then Curiosity right there at the surface, we can measure the atmosphere and tell how much of it has been lost. And one way we do this is with a particular type of gas called argon. So we have argon in our atmosphere. It's the third most abundant gas in our atmosphere. There's your trivia fact for today. It's also the third most abundant gas in Mars's atmosphere. And just like a lot of compounds, there's a heavy version and there's a light version. So anyone heard of like carbon-13 and carbon-12, same sort of thing. So there's heavy argon and there's light argon. And if you have all that sort of atmosphere lost to space, usually the heavy stuff is left behind preferentially, right? It's just harder for the heavy stuff to get sent away. The light stuff gets sent away first. And so that ratio, whatever ratio of heavy to light was there originally, that got kind of changed over time, right? And it's changed on Earth, it's changed on Jupiter, it's changed everywhere. And on Mars, it's changed in a very particular way that shows that it probably lost almost all of its atmosphere to space. And because of having MAVEN there and having Curiosity at the same time, we're able to tell that. Similarly for water. Water has a heavy version and a light version. Hydrogen does. And so we can tell that ratio right now is really high, a lot higher than Earth. It's way up here. It's about 6 times seawater here on Earth. But by measuring with Curiosity, by digging into that soil, and then measuring, because the soil was created a long time ago, billions of years, we know that ratio was much lower billions of years ago. So it's changed over time. And it's changed because over that history, from when that rock was created until today, Mars has lost an absolute ton of its atmosphere. And so 3 billion years ago, a lot of the atmosphere was still there, and a lot of the water was still there. And between now and then, it's all gone away. So in Yellowknife Bay here, we had a really remarkable find so early in the mission. I think that was the key here. 3 months after the mission was sent, we found that Mars at ancient times was capable of supporting life, and not exotic life, like very common life that we'd have in drinking water here today. Anything that's in here could have survived in Gale Crater 3.5 billion years ago. There was the water, there was the chemical ingredients that we know life needs, that was key, and we've had even sources of energy. So different microbes need different sources of energy to live on. It just doesn't need to be photosynthesis or eating other animals. There's different things that life can do, and that source of energy was there. So the key takeaway here is that at the same time that we know life was forming on Earth, so we know 3.5 billion years ago there was microbes living on Earth in environments very similar to this, where you had chemical ingredients necessary, you had sunlight, you had open water, and we know that life was forming on Earth at that time, 3.5 billion years ago. And at the exact same time, Mars had that same sort of environment. And we don't know if there was anything living there, but it could have. You could have transported any of the microbes that were forming on Earth at that time to Mars, and they would have been perfectly happy. You could have transported a trout from today to Mars 3.5 billion years ago, and the trout would be perfectly happy swimming around. Because the water not only was pH neutral, it was clear, it was clean, had all the different chemical things that life needs. Low salinity, it wasn't particularly salty. So we kind of hit pay dirt very soon after the mission landed. But again, we didn't sort of stop there, because the whole point of the mission was always to climb this mountain and see all these different layers of rock that have been deposited over long, long periods of time. And so we started driving, and we've driven a long way. We've driven 20 kilometers now. And so here's just sort of an image here crossing a little sand dune here called Dingo Gap. We drove in amongst these different buttes. So there's the rover tracks here. I like seeing these little sort of circle patterns. So when the rover turns, it kind of creates a circle in the dust because the 6 wheels together kind of turn in conjunction. It's got all-wheel drive, so it can all turn at the same time. And you can see these little turn marks here as it winds its way down, and there it is again from orbit. And so we found other evidence that the story of water in Gale Crater was much more complicated. It wasn't just a stream flowing into a lake. There was probably different episodes. So there was long periods of time where this lake was present and this river was flowing. And then probably it would dry out. And then probably the lake would come back. And then other times there was groundwater kind of coming up from underneath. And so we found these different layers of sandstone and other materials that show that they were deposited by water, standing surface water, at different times in Mars's history. Similarly here, so you have these different layers that are sort of tilting upward toward the Mount Sharp, that center of Gale Crater. And so you can imagine here you have this lake kind of overflowing here, you have rivers flowing into the lake, and you have different sort of rocks deposited at different places. Here you have more lake-like deposits, and here you have more river-like deposits that are farther up the flow. And so that sort of combination of being able to driving across all these different layers kind of gives us that full picture of how water interacted on the surface. And of course the chemistry. So you see these little white veins here that are mixed in the material. So you have this rock material, and water kind of flows into and percolates through, like a coffee pot, percolates through these rocks, and they interact with the materials, and they leave different minerals. So on Earth you get these things all the time, and there's things like gypsum and other rock materials that get left behind as water percolates through and kind of chemically reacts with the rocks that are present in the first place. And so we saw these all over the place as we drove past. Here too, we saw the sort of a difference of 2 layers here. So we had mudstones down here. So if you imagine, has anybody ever swam in a lake? Kind of not an ocean, but a lake, kind of mucky and muddy on the bottom, right? Pretty gross if you actually kind of walk around for the most part. But that's because you have all this different material that's sitting in the lake and then kind of settling down over time and creates that sort of mucky bottom. And this is what mudstone is, basically. If you then take all that lake away and let it evaporate for a couple billion years, you're kind of left with this dry, craggly mudstone. And up here you have sort of sandstone. So you have sand dunes that eventually get kind of hardened into rocks over long periods of time. And so you could see here, at some point we were at the bottom of a lake, and then eventually sand dunes kind of came over top of it, and then those hardened and those disappeared. And then we sort of went through these different periods of time where water was interacting in different ways. So in that mudstone, you see this sort of cracking, and this is exactly what you get. Have anybody been to the desert and seen right after a rainstorm, you kind of get these little wet spots that then dry out really fast, and they kind of leave these little cracks on the surface? That's exactly what this is. You get these little cracks on the surface when the material dries out after being wet previously. And so here's sort of a version of that here on Earth. You get very wet surface, and then it starts to dry out in the sunlight, and you get all these different little cracks form over time. More evidence chemically that that Mars was habitable and Mars had water interacting it was these different veins I talked about just a minute ago, and the particular chemistry in there called boron, particular element, again indicates that the way that the boron's interacting there in the rock, that these materials were emplaced with water flowing, and they were different amounts flowing at different spots along Gale Crater. So, all right, I've told you that story. Now let me tell you what I actually do. So if I've convinced you that I'm a geologist, I've done my job, and I've fooled you all very well, that's not what I do at all. This is what I do. I study the atmosphere of Mars with Curiosity. And the atmosphere in Gale Crater is extremely dynamic. It's really interesting. These couple of videos here just sort of show some of the things we see. And this bottom one has a really funny story. So dust devils are extremely common on Mars. The little whirlwinds that kick up dust that you see here, even on a windy day sometimes if you're out in a field or like on a baseball field, sometimes you see these little dust devils kick up. And they don't last very long. And they spread dust, and they have strong winds and that sort of thing. Well, on Mars, they are all over the place. And with the Spirit rover, we saw them every single day, just about. They're extremely common. We've seen them even from orbit. They're so tall, you can see them from orbit. They cast shadows on the surface, and they leave little tracks, dark tracks, where they've moved dust around on the surface. And so for the first couple of years of the mission, we were dedicated to looking for these dust devils. And we stared off into the northern side of the crater, looking all the different time. Saw maybe one. And it was like really, you have to really stretch the heck out of the image to even convince yourself there was one there. And so a couple of years later, we said, hey, you know what? We landed in a place, the only place on Mars, it seems, that doesn't have dust devils. And then someone said, well, why don't we look in the other direction? And said, okay, let's look in the other direction. And then here they are, all over the place in the other direction. So all we had to do was turn around, and we would have seen them. But no, we didn't turn around. We were dedicated to looking off to the north. But here they are, all over to the south. And so these dust devils on Earth, are, maybe like 50 feet high, something like that. These can be the size of like an F5 tornado. I mean, these are big, like 20 kilometers high sometimes. These are big, massive, giant things. Now, the force of the wind on Mars is so much less. It's not like they would, pick up your house and send you off to Kansas or anything like that, or to Oz, rather. But they're pretty strong, and they're really important for how the atmosphere actually works and cycles. And so they're just all over the place now. We're seeing an absolute ton of them. And actually, the season on Mars right now is when we start seeing a lot more of these. So we've started looking for these again a lot more, because we just left the cloudy season on Mars, and we're entering sort of the dusty season. And so these are images of clouds on Mars, and these are just like cirrus clouds here on Earth. Now, if you were standing in Gale Crater and looking up, you probably wouldn't see these very often, because they're very thin, and they're probably hard to see with the naked eye. So we kind of stretch the heck out of the image here, and you can see them very clearly kind of passing overhead. But they're very wispy, just like cirrus clouds on Earth. You see little structures in them sometimes. They're pretty exciting to see. And we, again, just left the cloudy season, and now we're entering the very dusty season. So we've been on Mars for 5 years, and now we are finally really climbing the mountain. So this was actually an old image. So we are up right about here right now. So we've climbed about 300 meters or so of elevation since we first landed. And we're finally entering these different types of rock units that sort of chose Gale Crater in the first place. I mean, that's why we went here. And we're finally now, after 5 years and 20 kilometers of driving, finally reaching these places. And we're up high, and we can look back out over the crater and see kind of where we came. And I thought this image was just remarkable. This was not taken too long ago, because it's in the clearer season on Mars when there's less dust in the atmosphere. Because in a couple of months, you wouldn't even be able to see here the edge of the crater, because it would just be too dusty. But you see here, this is where we landed. This is Yellowknife Bay, where all that evidence of water was found. And we crossed this dune field a couple of years ago. And now we're up here on this ridge that's very rich in a material called hematite, which again is something that on Earth is very commonly emplaced by water. And we're finding lots of evidence of that here as well. But again, it's a different story. The story is much more complex than what we thought it was originally. There's lots of different ways that water interacted, lots of different ways that the environment was habitable at different times over the history of Mars and over a long period of time in Gale Crater. So this is our route, and this is as of about a week ago or a little more. So here we are way up here when we landed. You see, that's just the distance we drove to get to Yellowknife Bay, where we found all this evidence of water. And we've driven all the way down here now. And so here's this ridge called Vera Rubin Ridge that we're sitting on now. And then we're kind of moving off into this next area here, probably later this year, over the summer sometime. And so I'm replaying this episode or this slide here because I want to point out clays here. So clays are really what has been exciting for the geologists for a long period of time, because clays form with water present, and they're really good at preserving ancient signs of life. They're really common on Earth, where if you find fossils and things like that, clays are a great place to look for them. And so we're finally just about to get into the area of clay. So this is the clay unit here that has yet to be named. We're kind of overlooking it here, and we're going to be heading into this area later this summer. So the story is certainly not over, and I think there's a lot more that we're going to learn here over the next couple of years. And hopefully we'll keep driving along, because there's a lot more mission to do. And I encourage you all to follow along. This is the Twitter handle. Every day that we have operational planning, someone writes a little blog about what we do. I'm one of the people. About 3 times a month, I write the blog about what Curiosity is doing. And so I encourage you guys to check that out. And I'd be happy to take any questions you might have.
Thank you very much. And he will repeat the questions so we all hear them.
When you talk about the dust storms,
Yeah.
when you consider that the atmosphere is just 2% of Earth,
Yep.
it's always what I've heard. How is it possible that you're lifting anything, or is that a breeze you can even feel when you talk about storms?
That's a great question. So the question was, with the atmosphere being so thin, how can you have enough force to lift dust off the surface? So that's a really good question, because for a long time people didn't understand. So we saw like evidence that dunes were moving, and we said, how are dunes moving? Because we, just based on physics, you should know what kind of force is required to start a particle of sand moving along the surface. And it seemed like you would need just insane wind speeds, like 200 mile per hour wind speeds for that to happen, which obviously should not be occurring very often. And so with a little bit more sort of refined work and looking a little bit closely, it looks like you still need very strong winds to get something to start going. So that first sand particle to start moving, you do need something very strong. Maybe not 200 miles per hour, maybe 60, 70 miles per hour, somewhere in that sort of range. But once something moves, then you don't need that sort of force to continue it to move. So then you can drop down to a much more common wind speed to keep it moving along. And so the way the physics works there on Mars is a little different than how it works here on Earth, where you sort of need that speed to maintain it moving. But then Mars, that thin atmosphere sort of helps you out a little bit once it's moving, because then you can keep it going without too much more effort. And so that's how we think, you get a little sand particle to move. The sand particle kind of hits the surface and it splashes off little tiny dust particles. And then those get lifted into the atmosphere because they're much smaller and much lighter. And then they can just kind of go forever.
So how would you represent the Mars winds? Was it something you would feel?
Oh, right. So the question is, would you feel Mars winds if you were standing there on the surface? So if the wind was strong enough, yes. So the force is about a factor of 10 weaker for the same wind speed. So if you had a 100 mile per hour wind on Mars, you would feel like a 10 mile per hour wind on Earth, more or less. That's the force. So like the movie The Martian, where Matt Damon is lifted off the surface and a boulder is thrown into him and the radio tower impales him or whatever. It's not happening. And I love that movie too. And my wife was like, she's like, come on, is that really how it would be? And I was like, the one science they got wrong was the atmospheric science. But he knew that it was wrong. He needed a plot device. He said this in interviews. And he said that was better than aliens. So no, that would never happen on Mars. But yes, if you were standing out there, if a dust devil blew over you, you would feel something. It wouldn't knock you off your feet, though.
Has Curiosity been hit by a dust devil?
So the question is, has Curiosity been hit by a dust devil? Yes, it has. So we have a air pressure sensor on the surface on the rover, so we can see a little dip in the air pressure as the dust devil passes over, and you can also just tell because the amount of dust on the surface of the rover gets blown off sometimes. So this is what was actually really key. So Spirit and Opportunity were designed to last for 90 days. So Opportunity's been there for 14 years now, and so that's really good on your warranty, right? And the reason is because they thought, well, the mission is just going to die because the amount of dust would cover the solar panels, and eventually you just wouldn't be able to generate enough power to do anything. And so there's this nice, if you look at the power output from the solar panels on Spirit and Opportunity, you see this nice kind of steady decline, and then boop, and it bumps up. And it declines, boop, and it bumps up. And it's sort of reached this steady state now that they've been able to continue to work with because they constantly get a dust devil to pass over and blow off the solar panels. Not completely clean, not brand new from the factory clean, but clean enough to keep doing work. Yes.
The reddish that was
Yep.
found in the Viking missions, is that a result of the area that it landed in, or better imagery, or atmospheric imaging?
It's so the question is, why does the atmosphere look blue in this image, for example? And so all photography is fake, and that's why. Because this has all just been processed in a certain way. So it's called white balancing, basically, where they try to basically bring out the different tones of the rock better, because that's really what they're looking for. And so they white balance the image to bring out the different tones in the rock more, at the expense of making the atmosphere look very Earth-like. So if you look on these websites and go into the raw image files, you can see in some of the color images the atmosphere looks very pinkish and reddish like you'd expect. But when that happens, you wash out a lot of the differences in color in the surface. And so the geologists run things more than us atmospheric scientists. And so they kind of white balance it to bring out the contrast in the rocks more.
If everything is grayish below the surface and not that far, where did all the red come from?
So good question. So the question is, if below the surface is gray, where did all the red come from? And that is a question that people are still trying to figure out somewhat. So the reddish color is the dust primarily, which literally covers the whole planet at some depth, whether it's just a microns or even meters of dust. And so the dust has a lot of iron oxide, so it's rust. And that's why Mars is red, because it's rusty. And so that is still an ongoing question, is the whole planet basically producing this dust at all different spots, or are there certain points that are kind of preferentially producing it? And different people have different feelings on that topic. But wherever the dust came from originally, it is covering the globe. And it constantly cycles around between the surface and the atmosphere. And so the whole planet is covered in it to some amount. But below the surface, yes, there's probably just as much diversity in color to the rock that Earth might have. And so some of it's gray. Like I said, there's actually sort of a family portrait of the different drill holes that we've done with Curiosity. You can probably find this online pretty easily. And you can see that some are that very gray color like I showed in the image, and some have a much different color, or even a combination of colors, because the different rock materials they're drilling into are unique.
Where the jets blew the surface, it looked like it was darker anyway. Some of the dust would have been blown off.
Right. So the question, when the rover landed and it kind of looked bluish on the surface, again, that's sort of the blue is probably more of an imaging processing, but it certainly was darker because the dust got all blown away. And so you saw the native rock color beneath the layer of dust. And the dust, gets in the way of a lot of the measurements. So like Sojourner went up to all these different rocks and had that little instrument that kind of sniffed them. Well, you know what they detected? Dust. That's what they detected. Every rock was made of dust. And so with more knowledge, so Spirit and Opportunity had this little tool called a RAT, Rover Abrasion Tool, which basically kind of ground the rock down as much as possible to get rid of that dust so they could actually measure what the rock is made of. And then Curiosity has like a brush that'll brush the dust off. The little laser beam on Curiosity will make a few blasts to basically clear the dust off a spot before they start measuring. And then, of course, the drill can get beneath that. So we have tools now to get away from the dust because the geologists don't find it as interesting as I do. Yes?
So you have indicated that there is particular seasons, cloudy seasons and whatnot. Have you then identified systems and streams, much like what we have here on Earth, like that happens in the Pacific and in the Atlantic, that would indicate those weather patterns?
Right. So the question is about weather patterns and whether they are similar to what we see on Earth. And so the answer is in a lot of ways, yes. So there are storm systems that for all the world look like a storm system, in wintertime here, with sort of a big comma head and a big sort of front, kind of passing down to the south. So Mars will see things like that very often. There's some differences, though. They're not quite as chaotic on Mars. Mars' atmosphere is much more regular. It doesn't behave as chaotically from year to year. So if you were on Mars, on a given day, and you went 1 year later, particularly if you're in the first half of the year where there's not a lot of dust storms, the weather's going to be almost identical, 1 year to the next. You're not going to get a lot of variability. Like, hey, 1 year it was warm this day, and next year it was cold this day. Like this April has been chilly, right? But last year was warm. And Mars, you're not going to get that sort of variability. It's just a much more regular climate just because the atmosphere is so much thinner, and there's just not the water around in the atmosphere to drive those differences. There's not something like an ocean that's holding all this heat that then the atmosphere can sort of interact with in complicated ways. With just the atmosphere there and a very thin atmosphere at that, it's much more driven just by the daily cycle of heat from the sun, because the sun heats the atmosphere during the day, and at nighttime all that heat goes away, and the atmosphere essentially hits a reset button. It's like, okay, next day it's a brand new day, start again. And next day, sun comes up, dust devils kick up, clouds might be there in the morning, clouds go away, dust devils kick up, sun gets turned off, and then the next day is a recycle. And the only big difference is in the dust storms. Sometimes the dust storms can last for days and days. And those are sort of the one, chaotic event that Mars's atmosphere has.
Are those effectively those sandstorms, right? Dust
Yeah.
storms? Then I'm assuming those are fairly predictable in that, like, you can see when they're occurring either because of some sort of system that's just going around the planet or based on circumstances that happened the previous year.
So, right, the question is how predictable are the dust storms? And the answer is we know what seasons they preferentially occur at, and they know where they preferentially occur. But we have no predictive capability to say, oh, there's going to be a dust storm here in 2 days, or this small dust storm is going to become a much bigger dust storm, next Wednesday. There's no predictive capability, and people are starting to look towards that sort of thing with model. I do some modeling, and people are sort of starting to get towards that, but there seems to be some challenges to that don't exist for Earth forecasting. And a lot of it boils down to we don't understand why storms form in certain places at certain times in the first place. And so, and kind of going back to this gentleman's question, there's dust in different places in different amounts. So maybe all the conditions are right at this place, but there's not much dust on the surface. So you just have this sort of, whatever spin in the atmosphere occurs, it doesn't create a dust storm. But then the same sort of thing happens over there where there is a lot of dust on the ground, and suddenly you have a big dust storm kick up. And that's the level of fidelity that we don't understand.
What's the temperature range roughly where Curiosity is?
Mm-hmm.
And does Curiosity work 24 hours a day, or does it have to shut down at night?
So the question is, what is the daily temperature range at Curiosity, and does the rover shut down at night? So the first question is, the temperature range is huge. It can be like 100 degrees Celsius in a given day. It'll get down extremely cold at nighttime, down to well over 100 degrees below zero Celsius or Fahrenheit. And then in daytime, it can get up to freezing, even to like 65 degrees, like right at the surface maybe. But then again, when the sun gets turned off, the temperature just drops. There's nothing there to hold the heat, and it'll get extremely cold. And so because of that, yes, the rover primarily does not do much at night. And when it does, it ends up being a big burden on power. So there's only so much power we have every day. And that radioactive generator that we have essentially trickle charges the battery all the time. And so we run the rover off of the battery. And so we kind of deplete the battery, and then we basically tell the rover to go to sleep, and the rover's battery can recharge. And then we start doing something, and the battery goes down and so forth. And so at nighttime, if you want to do anything, you have to run the heaters really, really hot, because every little instrument and movement has its own heater, and all those require power. So if you want to take pictures at nighttime, or if you want to take measurements at nighttime, you need to run heaters, and those take a ton of power. And so we typically don't do much at night, sometimes, but typically not. Right. Okay. So the question is, the atmosphere of Mars has been depleted over time as the atmosphere was lost to space. Are we seeing any of that over the amount of time that we've been on the surface? No. So the atmosphere has been about the same every time we've measured it. There's been a little bit of variation, but it's all kind of within the noise. So we can measure. So the MAVEN mission is measuring how much is being lost per day, essentially. And it's like a couple kilograms per day of atmosphere is being lost to space. And so we can measure that, but you can just sort of do like a back of the envelope math on that, and how long would it take for us to sort of see any difference? And it's still just, millennia sort of thing before we would see any difference. Yeah. So actually, when we first landed, we thought we maybe saw some differences because Viking did the same thing 30 years ago. And we thought maybe we saw some differences between Viking and Curiosity. And now we sort of think why we know basically that our measurements are better. But so people wondered about that very thing, but it seems like the answer is just measurement differences.
So could the frozen water on Mars be changed to liquid water?
So the question is, could the frozen water on Mars be changed to liquid water? Yes, certainly. It just needs heat, basically. And there are certainly particular places and particular times of year where the air is warm enough and there's enough air pressure, because that's the other key that people on Earth don't really realize. Not only for liquid water do you need it to be warm, you need to have enough air pressure to support liquid water. And Mars is right near this point, this very interesting point called the triple point, where it's very close between the boundary where water is either gas, solid, or liquid. And the mean condition, the average condition on Mars is very, very much almost at that point. And so, yes, in certain places you could have liquid water even today. And so when the Phoenix lander, this was back in 2007, the Phoenix lander came down at near the North Polar Cap, not at the North Polar Cap, but pretty close, essentially equivalent to like the Canadian high Arctic. And it landed there, and there's ice right below the surface. And I mean right below, like within an inch or two of the surface is essentially pure ice. And so because when its rocket engines landed, it blew off all that dust and saw this little tiny skating rink right beneath the surface. And so the camera kind of looked underneath of the lander to look at that ice, and it saw all these little droplets on the landing legs. There was liquid water droplets on the landing legs of Phoenix. And it wasn't because the water was pure and it was 32 degrees or warmer. Because if you mixed water with different types of salt, just if you imagine like seawater doesn't freeze at 32 degrees. Seawater freezes at like 29 degrees for the most part. And so Mars's soil has a lot of salt in it and different types. And so the salt makes it able to be liquid at colder temperatures. And so this is probably what happened. There was little bits of ice got kicked up, mixed with the salt when the lander hit the ground, and it landed on the legs, and it got warm the next day, and it melted. And so you had these little droplets of water on the surface. And so if you want, though, the whole polar cap to melt, then you just need a lot more. You need a lot of heat. You need a lot more heat because most places on the planet are always going to be either too cold or not have sufficient air pressure to have liquid water.
And also, might there be some caves on Mars?
So the question is, are there caves on Mars? Yes, there are certainly caves on Mars. They've seen from orbit signs of like volcanic tubes. So if you go out like in California, there's these like volcanic lava tubes where lava used to flow through. Hawaii has these as well. And you can see these sort of, a lot of times they'll get like a little hole in the top called like a skylight. And you can kind of see down that there's probably a lava tube underneath there. The moon has them also. And so they've seen these from orbit around some of the volcanoes on Mars. And a lot of other caves on Earth are sort of obviously formed by liquid water kind of flowing through. And so, probably there are those types of caves somewhere. Of course, we just can't see them from orbit. And we haven't been on the ground near the entrance to one. And even if there was one, there was no way we would drive into it. So, yeah.
Well, thank you all for coming. If you want to talk, you can come on down while we're shutting down. Thank you so much.
Thanks.
This has been a presentation of the Library of Congress. Visit us at loc.gov.